Hello and welcome back. In this video we'll talk about classical machine learning and what we mean by this is essentially everything apart from neural networks, so clustering, decision trees and bagging and boosting methods. So let's start with clustering. What is clustering? Clustering is one of the unsupervised learning methods. That means we don't have predefined labels and is typically used to discover some structures in data. So for example, let's take an example we all know, like items in a supermarket. So we may have apples and pears and other fruit like strawberries and meat like sausage and freshly cut meat and so on. And intuitively we can understand that different kinds of apples are closer together by some metric than apples and pears, for example, or fruit is more related to each other than fruit and meat. So what we do here is we establish classes and find items that within such a class they are by some metric closer to each other than items outside the class. So what does close mean? That means we need some sort of distance metric. Think about some metrics. What kind of metrics do you come up with? The simplest one we typically use is the Euclidean distance, essentially the length between 2 points. It's essentially the L2 norm, or the squared difference between all the coordinates of the points. We could also have the Manhattan distance. Essentially here, think of New York, and this is where it's also got its name from. In Manhattan, it's the length between 2 points, but we don't go as the crow flies, as we might say, but we need to move on a grid. Like for example, instead of flying from one skyscraper to the next, we would have to take a taxi, and a taxi can't of course go wherever it wants to go. It needs to adhere to the streets. So we define the Manhattan distance as the length between 2 points on a grid, and you can see some examples here. In red you have the Euclidean distance, that's the shortest path between 2 points as the crow flies. And if we can't do that, we need to move on the grid, and you can see two equivalent ones. There are also different metrics. One of them is the cosine similarity, and that is the similarity between two non-zero vectors. That is, for example, important when you come to machine learning and embeddings. Some popular clustering approaches are k-means and others. We'll start with k-means. And the algorithm is based on the Euclidean distance. So you use a data sample to define k centroids as initial clusters. So k here, the number of clusters we want to have, is a free parameters. So we need to know this. Then we assign each data point to the nearest centroid, and then move these centroids around and assign the data points. And we repeat this until we have converge, that means no more change, or we've reached the maximum number of iterations. To do this, we optimize the sum of squares. This is what we mean by it's based on the Euclidean distance. So we sum over all data points and all clusters and find the shortest path between all data points and all clusters. Let's try this with an example. So here we have 3 overlapping clusters. Let's find 3 clusters. In Euclidean space, this means we have spherical clusters, because in Euclidean distance we find the shortest distance between 2 points, and that naturally leads us, in the ideal case, to a circle. So the data on the left, of course, we don't know which point belongs to which cluster. Of course, since we've generated these clusters here on the right, we see the ground truth, and we can see what k-means does if we have 3 clusters as a free parameter. You can see that this works in general quite well, as we would expect, since at least 2 of the clusters are well separated, but you can see that the overlap regions are difficult. The clustering algorithm has no way of knowing if a point should belong to one cluster or the other. Since k is a free parameter, we can also tell k-means to find 4 clusters. Of course, we don't expect this to work particularly well, since we know that we generated the data with 3 clusters, but here you can see the result. It found 4 clusters and 2 clusters on the top right. These are the ones the k-means algorithm had to find, although it doesn't quite work. Another approach is hierarchical clustering. In k-means we saw that we have spherical clusters and no relationship between the entities, but often we do have relations between clusters. So we can do two ways. We can go bottom up or top down, and this is then typically visualized as such a dendrogram. Let's take our supermarket example. We can either start from the top and say we have all the food stuff in the supermarket, and then we split it into, for example, fruit and meat, and the fruit into apples and pears and strawberry, and then the apples again into individual classes of apples and individual classes of pears, so that the lowest level would go back to the individual fruit items. The highest level would just be everything. In between we do have hierarchical relationship. You can of course go also bottom up, so we start with each item and then find common metrics or common aspects between these things. For example, all apples belong more naturally together than apples and pears, and all pears belong together, so we have apples and pears. Strawberries don't quite fit the bill quite yet, but they belong into the fruit category, and then once we have the fruit we can also group the meats together, and then on the highest level again we have all food stuff. We've seen that k-means in k-means all clusters are assumed to be spherical. This is part of the Euclidean distance. Of course, in most realistic scenarios this is not quite fulfilled, and we also need to assume with k-means that each point belongs to a single cluster. So the next step in making this more general is to go to Gaussian mixture models. Here we replace those circles by Gaussian, and this is why it's called Gaussian mixture model. So we can account for variance, that means we can handle oblong clusters, and we can also then assign a probability that each point belongs to a cluster. The optimization is done with the expectation minimization algorithm, which we don't discuss in detail here, but you can find it in the literature, of course. One more general approach is called dB-scan. It's called density-based spatial clustering of applications with noise. And one of the key points is already in the name, the N for noise. So here we assume that not each data point must belong to a cluster. It can also be part of some sort of noisy data. dB-scan has a number of advantages. For example, we don't assume spherical clusters or hierarchies. So we assign clusters by the density of points. How does this algorithm work on a very high level? So we define core points with minimum of number of points within a given radius epsilon. So the core points here are the green squares. And we say we want to have n points within the proximity. So for example, in this case here, the border points that we also need to define. The border points are those with smaller endpoints but within the core. So the core idea is we have the core point with a number of points there and a radius, and within this radius we have the border points as well. So now we define a cluster for each of those core points and assign each border point to a cluster of the corresponding core size, and then we iterate. So this way we can find clusters. And note, we don't need to specify the number of clusters beforehand. The key point is that we define the radius and the number of points that constitute a cluster, and then the algorithm finds the suitable number of clusters. Right? So we, unlike k-means, we don't specify the number of clusters we have. You also see the noise points. These are the open circles, and they are not assigned to any cluster. So that means that these points are not taken into account when we build the clusters, and as we discussed before, this has the advantage that noise can be incorporated in the data as well. So how does this then work when we compare all these three? We've already seen the ground truth plot for k-means, and we've seen that in particular the overlap region was very difficult. We can see for Gaussian mixture model in this example it also works quite well because the overlap region is better handled perhaps, but we can also see that the difference between the k-means and Gaussian mixture model is not that large because the clusters are roughly spherical since we created them this way. dB-scan looks a bit different, and you can see that here the clusters are a bit more separated. We also have 6 clusters. You can see that there are 3 very small clusters, and the 3 larger clusters that correspond to the ones that we would expect. And you can also see that there are a number of noise points that are not associated with one of the clusters. Now, of course, we generated the data such that each data point belongs to a cluster, but in reality we would have some noisy measurements, for example, and this is handled by the VB-scan algorithm. In your application, when you use dbScan, now you would have to discuss a bit if you would actually use those small clusters, if they make sense, or if you have to remove them or merge them with the other clusters. In this example, we know that they are not real, that they're an artifact of the approach, but in your application, you may find that this is either useful or not. Let's discuss a few more complicated examples, right? These spherical relationships between those data points were very simple for all of these algorithms, but let's see how these algorithms handle more complex ones. In particular, these half-moon shapes cannot be linearly separated, so you can't draw a single line. And this is where the assumptions of the different clustering algorithms come in, make it, for example, impossible for the k-means, but also for the Gaussian mixture model, impossible for them to find the appropriate clusters, as you can see. Intuitively, for us humans, it makes sense that we have a half-moon open and close, or up and down, and k-means, because it assumes a spherical shape, and you can see this very well, doesn't allow to separate those two half-moons. And with the Gaussian mixture model, you can also see that maybe these assignment of clusters are a bit oblong, but essentially it also cannot handle this case. Whereas if we use dbScan, it finds the two appropriate clusters. Now, you go to the companion notebook and try it for yourself. Let's move on to decision trees. What are decision trees? They are a supervised machine learning algorithm. That means we know the true label or target or the true assignment. They're typically used for tabular data that we want to map to a prediction. So each event is described by multiple variables. They're also called features, feature variables or attributes, independent variables if you come from the statistics point of view, descriptors if you come from material science, for example. So each community has a bit their own terminology. It's a classical machine learning algorithm in the sense that we need human experts to derive these feature variables. So in the end, you want to end up with a table of variables and values, right? And we need to come to these variables by some means, and typically that means we need to exploit the human expertise to create those variables and then use the machine learning algorithm or decision trees to map these variables to a prediction. As the analogy goes, the decision tree is defined by branches and leaves. So what do we mean by that? Let's take a very simple example for a binary classification and say what is, for example, a valuable customer. And we could have some defined features that some expert has derived for us, for example, the available income for such a person, the number of purchases they have done in our store last month, the amount they spend, and these kind of variables. And then we can build a set of rules. Is this a good or a bad customer? And you can see one example here. We start from the available income and then make a split. If the income is very large, it goes into the right branch, otherwise into the left. And then we look at the number of euros spent and the number of purchases and so on. And by repeating the process, we can build our tree. And the final layer is good customer or bad customer. So this is all very simple. So we build a decision tree by choosing a root variable on the top, then define the split variable, then choose the next variable, define the split, and so on. So we need to define and decide upon the sequence of variables, and of course we can use those variables more than once, the values at which to make a cut or open a new branch, how many branches we want to have maximum, and how many events we need to end up in the final leaves and the final layer. Right? If we make this tree very, very fine, we end up with only one data sample per leaf, but maybe we want to be a bit more robust and have a few more. Training these decision trees then is based on some metric if we don't do it manually. So what we want is the best variable and the best split at each point. The simplest thing we can do is the residual sum of squares, since we have labeled data where we know the truth. So we find the tree with the lowest number of wrong assignments. And then there are two other metrics that are frequently used. One is the Gini impurity and one is based on the information entropy, and they essentially measure the orderedness in the final tree, right? So how often would a label for random data point be incorrect if the label was assigned according to the distribution, or in particular for the information entropy, we aim for a high degree of order so that if we reach the final branch and leave, we don't make a mistake, we only have one class in each. In practice, most trees, I would say, are typically now trained with information entropy, or if it's a regression approach, with the residual sum of squares. So think about pros and cons for decision trees, and what can we do about this. Such a single decision tree is very easy to understand because we have simple rules, and they can, or they could at least, be made by hand. That means such a single decision tree is fully explainable in the sense that at each point of the algorithm we can understand how a decision was made. It's also easy to handle outliers. If we, for example, have a cut greater than 10 in number of purchases, it doesn't matter if it's 10, 11, 12 or 2000. However, since we just use the variables with cuts, we ignore the correlations. And because variables are in general correlated, each of these splits influences the behavior of all other variables, so that means that the order of variables matter. Remember that when we started with a decision tree, we needed to pick a variable to put as root variable. So now, because the variables are correlated, that means that if we make a choice, it may not be optimal because we need to make some cuts and decisions on the values later on, and we could have obtained a different result if we had started with a different variable. So that all means that a single decision tree is quite prone to overtraining. We could, of course, make a perfect decision tree if we had too many branches and too few items in the leaves, right? Because then each leaf is pure if there's only one data point in it. So we need some way to address all of this, and one way is, for example, to build forest. This brings into ensemble learning, which goes back to bagging and boosting. That means we have a better performance, but also comes at the downside that we have less interpretability, because a single tree is now very easy to understand, as we just said, but if you have many trees and combine their output, it's like looking at a forest, and it's not so easy anymore to understand what's really going on. So as we move on, we first need to introduce the concept of a weak learner. So a weak learner is some machine learning algorithm that has a mediocre performance with known weaknesses, like, for example, our single decision tree. However, it's easy to set up and train and so on. So this is our starting point. And how do we mitigate this? Well, we take many of these weak learners, and this is what we call an ensemble. So we combine multiple versions, variants, different kinds of algorithms even, and then build such an ensemble predictor. And this we do with the idea that this combination of many weak learners is very powerful because their downsides compensate each other. So how do we combine them? For example, if we do a classification like our good or bad customer, we could just do a majority vote of all of these algorithms in our ensemble, or if it's a regression, we could take the mean of all predictions. So let's go into some specifics of how we could build ensembles. Bagging is one approach where we train multiple algorithms on subsets of the data and combine them in an example. So for data, we take our original data back, let's have this illustration there, and take n different variations of the training data. So how do we do this? We take an element out of our data set and put it into our new bag, like a copy, because we put the element back into the original. Now, then we repeat this until we have the same number of events in the new bag as in the old one. Because we put events back, events can now occur multiple times in the new bags of our data. So we build many bags, and each bag is slightly different because it's very unlikely to near impossible that we will just copy the original data set. So all of these variations mean that some events are double, triple and even more. However, that doesn't reduce overtraining because no single algorithm trained on each of these bags of data now sees the whole data. We can do the same with the features, right? So bagging again, the idea is we train multiple algorithms on subsets. Before we talked on data, now we talk on features. Now for features, it's also called the random subspace method, right? We take n different variations of the features, take an element of this feature set and put it into a new bag, put the element back into the original bag, repeat until the new bag has the same number of elements as the original one, and now of course the features can be there. You can see that the approach for features and data are exactly the same, it's just that we do different things, right? And again, this reduces overtraining because no single algorithm sees the whole set of features. We have two approaches where no algorithm in our ensemble sees the whole set of data and no algorithm in our set of ensembles sees the whole feature set. And this really is what random forests are about. They combine both approaches, both the bagging for data and the feature bagging, and then build a forest of tree, the random forest, out of these. Boosting is a different approach to tackle weak learners and combine an ensemble into a strong and powerful one. So here we take a sequential approach, right? The idea is that we train a weak learner and we know that because this is a weak learner that we will have some wrong results. Now we identify on our training data which results are wrong, and then we train a new weak learner to compensate for those. Because it's a weak learner, we don't expect that the second part corrects all mistakes, so we probably need to iterate this a couple of times, right? So the idea is we start with one weak learner and the next weak learner compensates the errors of the first one and the next weak learner compensates the errors of the previous one and so on, and we repeat the process until we are satisfied with the performance. So there are many algorithms and the most performant one are now these boosted decision trees. They are very powerful for tabular and structured data, and they typically provide good performance for out-of-the-box application. The downside is that they're not very explainable, but if you just use them, they are the go-to method for most cases, and there are a few popular implementations that you probably have heard of already. There's XGBoost, there's LightGBM, and there's CatBoost with that improved functionality for categorical features. Again, there's a companion notebook, so please go ahead and